So welcome back. In the previous session we studied about the state machines. What is the state machine? How we represent the state and the transition which are available in between the states. We studied. The continuation we are not discussing the continuation topic, that is history states. Next one is the history states. History state. What is a history state? History state will be representing. History state will be representing for what? History states is the state that remembers the last sub-state. What it remembers? History state. History state will be remembering last sub-state. Last sub-state that was active prior to leaving the composite state. That will saving the last sub-state information. Okay. So history states are used if we want to transition to active the last substate. Why we are using history state? History states will be used if we want to transition to active the last substate. Where the transition is activated in the last substate, from that the history state will be used. Okay. Show a transition from outside the composite state directly to the history state. The first time we enter a composite state, it has no history. If it first time composite state enter, that do not have history state. Okay. So history state will be used last substate information which stores. Okay. History states are of this is the history state. Last substate information which will save it. Okay. So history will be representing H. See, history states are of two types. Two types of history states. Shallow history, denoted by H. Shallow history. Deep history. Deep history will be denoted by H star. Capital H star. Okay. Shallow history state is denoted by H, which remembers only the history of the immediate nested state machine. What is a shallow history? That will remembers immediate nested state machine. Immediate nested state machine. Whereas if you take the deep history state is denoted by H star, which remembers down to the innermost nested states. Immediate nested state which represents shallow history, deep history which represents innermost nested states. At any depth of innermost nested state which represents deep history, deep innermost nested states, that will represent. Okay. So deep history will be representing H star, capital H star. Shallow history will be representing H. Shallow history will be representing H. So if we have only one level of nesting, shallow and deep history states are semantically similar. Only one level of nesting. If we have more than one level of nesting, shallow history remembers only the outermost nested state. Deep history remembers the innermost nested state. Many number of levels are there. The history state, that is the levels of a particular nesting of states. And the state having another state. State having another state. That is shallow history will be remembering the first nested state, and the deep history will be remembering the innermost nested state. Okay. Next, concurrent substate, similar to the fork and join. Concurrent substate. Sequentially, substates are the most common kind of nested state machine. In the certain modeling situations, however, you will want to specify concurrent substates. Concurrent in the sense that you may have to split the one input into several outputs, and also you have to combine the several inputs into one output. Likewise, concurrent flow. Concurrent flow will be splitting like that. Okay. So take concurrent substates. See this concurrent substate from ideal state. At ideal state to maintenance state, only one flow is coming. So that one flow will be divided into many kind of flows. That is a fork, splitting one input into several outputs. So this is one flow, testing is one flow, commanding is one flow. Okay. Testing and commanding both two are concurrent state. Okay. Those two are executing concurrently. So the entire maintenance state is a composite state. Which has another many number of states. Composite states. So after getting the output of this composite concurrent processes are the states again which goes to output. Okay, many to one. Many outputs are came here. Those many outputs will be joined and given to single input. That is join. Fork and join. In state machine, fork and joins are there. So remember, fork, how do we represent a fork? Single input which comes and which flows many number of outputs. That is fork. What is a joining? Joining in a sense opposite. Many number of inputs are there. Among many number of inputs which joins only one output. Okay, this is a fork. This is join. Okay, this is join. Fork and joins are available in the state machine also, like activity. So those are also using concurrent substates. So common modeling technique. How do we model a particular state machine with the help of this modeling? Modeling the lifetime of an object. How do we model the lifetime of an object with the help of this concurrent state machine states? During modeling, we specify three things. What are those? Events and its order to which the object can respond. Events and order to which the objects can respond. How the object can respond. Response to those events, how it responds to that particular events, and also impact of the past on current behavior. So what is the past event on current particular event? So how it behaves. So those all minded, and we have to model a particular state machine. Set the context for the state machine, whether it is a class or a use case or other system as a whole. Okay. So if the context is a class or the use case, collect the neighboring classes. If we want to designing this state machine for a particular class or the use case of the neighbors, including any parents of the class and any classes reachable by the associations or the dependencies. So these neighbors are candidates to get targeted for actions and are candidates for including a guarded conditions also. So you may also modeling the context for the state machine, whether it is a class. Set the context for the state machine. If you are setting the context for the state machine, if you have whether it is a class or use case, you have to found what is the reachable for association or dependencies, whatever it may be. Depending upon the guarded condition, you have to specify. Okay, you have to specify. And next, common modeling technique. Set the context for the state machine. So, if the context is the system as a whole, so narrow your focus to behave of the system. How the system will be behaving with the help of context of the whole system. If you take. So, theoretically, every object in the system may be a participant in a model of the system's lifetime, and it's except for the most trivial systems, a composite model would be interactable. So, if you see, maybe a participant in a model, not only modeling to the whole system. So you have to divide the narrow behavior of a particular system. Theoretically, every object in the system may be participant in a model of the system's lifetime. So every object may be modeling in a whole system. So that and except for the most trivial system, some complete model would be interactable. Every model will be interactable, or every whole system may be of, sometimes it may active. Okay, so that is also, remember while you designing the state machines, establish the initial and final state for the object to guide the rest of your model. Establishing the initial state and the final state. So to guide the rest of your model, possibly state the pre and post conditions of the initial and final states respectively. So first of all, while designing the state machine, you have to found what is the initial state, what is the exist state, that is initial states and final state. So you found and decide are the events to which this object may respond. If already specified, you will find those the objects interfaces. If not already specified, you have to consider with the objects may be interacted with the objective your context, and then which events they may possibly dispatch. So decide on the events, based on the events which object may respond. Which object may respond. If you have many kind of objects, among all those objects, which objects will be responded for particular state, that has to remember, and which already objects interfaces you have to draw. You have to draw and specify particular object to the object that will related to a particular state. Okay, so you found, and second point is finding initial final state, and the third point is depending on the object. So what kind of that is what kind of states are evaluated for a particular object. If you are not found that object, you have to found that particular object and specify the interfaces for that object. If you are not already specified, you have to consider which object may interact with the object in your context, another object. So likewise you have to create state machines. Okay, starting from the initial state to the final state, lay out the top level states the object may be in. Connect these states with transitions triggered by the appropriate events. Continue by adding actions to the transitions. You have to draw first of all the states. After that, identify which state is going to be start first, which state is going to be ended at the end, final state, and you have to give the top level state in the object. Maybe in finding of the top level states, in that state you give some transitions, Identify any entry or exit actions. Especially if you found that the idiom the cover is used in the state machine. Identify the entry and exit states also. If any entry and exit substates available, okay. Expand these states as necessary by using substates. So using substates also you have to expand the existing states. Okay, substates, composite states you have to form. Check that all events mentioned in the state machine match events expected by the interface of the object. Similarly, check that all events expected by the interface of the object are handled by the state machine. Finally, look to place where you explicitly want to ignore events. If the events are not usable by you, you have to ignore those events also. So that events may be not done in the state machine. Check that all the actions mentioned in the state machine are sustained by the relationship, methods and operations of the closing object. Check all the actions. So trace through all the state machine, either manually or using some tools also. Check the against expected sequence of the events and their responses. Be especially diligent to looking for unreachable states also. So machines maybe get stuck. Unreachable states is any states are there. With the help of that state is never used in your system. That is unreachable state. Is there any unreachable states? You have to remember those unreachable states. After rearranging your state machine, check it against expected sequences. Again to ensure that you have not changed the object semantics. So with the help of object semantics, you may not be changed to the diagram. Okay. So diagram. So this is the actual common modeling techniques for the particular system. Okay. What is that? State machines. Okay. So now we move to know about the third topic. Third topic available in the particular unit 5. So events are there. What are the events we have? What are the signals we have? Okay, what are the state machines? State machines, how do we create a state and transition, and how do we model depending upon the object management. Now we move to processes and threads. Processes and threads. In this class, what is a process and how do we use the processes and the threads available in a unit number 5. Okay, let's start. So processes and threads. In the UML, each independent flow of a control is modeled as an objective. What is that object? Active object. Active objects. Each independent flow of a control is modeled as an active object. Each independent flow of a control. Okay. So an active object is an object. What is an active object? What is an active object? Active object is an object that owns a process or the thread and can be initiate control activity. What it initiates? Active class, active object. Active object will be initiate the control activity, initiating the control activity. So an active class, active object. What is an active class? Active class is a class whose instances are active objects. Active class is a class whose instances are the active objects. Okay. A process is a heavyweight flow that can execute concurrently with other processes. What is a process? Important. Process is a heavyweight flow. What is a thread? Thread is a lightweight flow that can execute concurrently with other threads within the same process or within other processes also. Okay. So process and threads. In this concept, we move to know about the active object. What is an active object? Active object owns the process and the thread. Active class owns the active objects. Process is having heavyweight flow concurrently with other process. Thread has lightweight flow concurrently having with other process. Okay, active. See, graphically an active class is rendered as a rectangle with thick lines. You know, process and threads are rendered as a stereotyped active classes. Process and threads are stereotyped activities. Attribute, it is name of the blackboard controller. Blackboard controller is the name of the particular active class. Active class attributes are there. Current knowledge source. Operations, other operations you mentioned here, and you mentioned the signals also. Signals. Signals also representing with the additional compartment in the active class. Okay. And next, classes and events. Now we move to know classes and events. Active classes are just classes. What are active classes? Active classes are only the just classes, albeit once with a very special property. Once with a very special property. Okay. An active class represents an independent flow of a control. Active class will be representing independent flow of a control. Active class representing independent flow of control. Whereas a plain class embodies no such flow. Plain class do not have flow of normal control, but active class having independent flow of a control. In contrast to active classes, plain classes are implicitly called passive because they cannot independently initiate control activities. See, active object will be representing is like this, thick border. See this thick border, active line. B is object name, blackboard controller object name. Passive object do not have thick border, normal border which have. Okay, blackboard controller, passive object and the active object. Okay. Active object representing independent flow of control, whereas passive object object will be representing what active classes and passive plain classes are implicitly passive. Okay, so see, representing features of active classes. Features of active classes may have instances, attributes and operations, and may participate in dependency, generalization, association, including aggregation relationship also. Active classes. Active classes have their operations, attributes and some relationships also which they have. May use any of the UML's extensibility mechanisms including stereotypes, tagged values and constants also. So stereotypes, tagged values and constants also using for active classes. May be the realization of instances also. Active classes may be realized by collaborations and the behavior of an active class may be specified by using state machine also. Okay. So standard elements, active class and events representing by thick line. Okay, standard elements, all of the UML's extensibility mechanisms apply to active classes. Most often you will use tagged values. Tagged values will be given in the square brackets, some expression, Boolean expression. So some information you gave into the square brackets. Extended activity class properties such as specifying the scheduling policy of the active class also. You may represent standard elements with the tagged values also. Use the UML defines two standard stereotypes that apply to the active classes. two standard stereotypes that applying into the active class, that is process and second one is the thread, process and the thread. Specifying a heavyweight flow that can execute concurrent. Heavyweight, I already defined. Heavyweight flow process have lightweight flow thread within the other process or other threads. Okay. And next, the distinction between a process and the thread arises from the two different ways of a flow of control. May be managed by the operating system of the node on which the object resides. The flow of control of process and thread will be dependent upon the operating system that particularly having the node on which the object resides. Okay. A process is heavyweight, which means that it is a thing known to the operating system itself and runs in an independent address space. Process will be runs in independent address space. Processes are never nested inside one another. Never nested. Processes are never nested. That means one process do not have nested into inner process, that do not have inner process. Okay. If the node has multiple processors, then true concurrency on that node is possible. If the node has only one processor, there is only the illusion of the true concurrency carried out by the underlying operating systems. Depending upon the processors, the processors will be used. The processors will be used. Okay. And next, a thread is lightweight. It may known to the operating system itself. More often it is hidden inside the heavier weight process and runs inside the address space of the enclosing process. Thread will be executing into the process. Okay. So threads are never nested inside one another. How? Processors do not having never nested, threads are also never nested inside another one. In general, there is only the illusion of the true concurrency among the threads because it's processes, not threads, that are scheduled by a node's operating system. Depending upon the operating systems also scheduling with the help of node, in a particular unified modeling language also, process will also not nested. Threads are also not nested. Okay. So communication, objects collaborate with the one another by passing messages. Objects how collaborates, types of communications is done with the communication passive object, simple class, active objects, active object, passive object. Okay. From passive object to simple class, only one flow of control, simple invocation of an operation, characteristics. From passive object to passive object, only one flow of control, simple invocation of an operation. Whereas if you take active object to active object, from active object to active object, inter-process communication is done. Inter-process communication like operating system. Okay. Synchronous call event, rendigious event, synchronous call event, asynchronous signal event. Calling event, that is the response, asynchronous, synchronous, asynchronous. Okay. So that will be given to the active object in between from active object to active object. From active object to passive object, that is normal simple object. So problem, if two or more objects pass control flow through passive object at once, hence synchronization is done. Here, you pass two or more objects, passive object control flow, at that time the synchronization is done. Synchronization. So whereas passive object to active object, passive object from active object, from passive object to active object, same as active object in IPC. So interprocessor communication, how it is done? That is also done with the passive, from passive object to active object. Only for problem synchronization is arise active to passive. Passive to active, automatically interprocess communication is done. Okay. So the event will be calling this as a call event, this as a synchronous event. Okay. So that is the communication. Okay. So synchronization. What is a synchronization? Synchronization will be explained later in the next class. At this particular time, we will stop this session. Okay. Thank you.